Hi there, I'm Paul Calleja. I'm the Director of Research Computing at the University of Cambridge. The Open Exascale Lab is an exciting new activity at the university, focusing on exploring new compute and software technologies that can be used to create upcoming exascale computing systems. So computing systems of the next size magnitude of 1,000 petaflops or so. The Open Exascale Lab is important because today exascale machines are currently out of reach. There are a lot of new technologies that need to be deployed to get us to that stage. So Cambridge has partnered with Dell and Intel. In fact, the lab is jointly funded by Dell, Intel and Cambridge to look at new technologies and how we can fashion them into very large scale compute systems that real life researchers can use. So you might say, why is that important? Why do researchers need access to systems which are 1 or 2 orders of magnitude larger than today's systems? Well, researchers tackling today's real world ground challenges like climate change or disease simulations, epidemiology modeling, clean energy. These big challenges need really large scale compute resources, and exascale systems actually promise to deliver those large scale compute resources so that we can tackle these really big problems quickly and in timescales that really make a difference in the real world. The Open Exascale Lab has chosen to look at a number of the key challenges that computer technology faces in getting to this exascale problem. So you can break the problem down into a number of key areas. The first area we're looking at is the software environment, the programming environment used to write applications that can scale across tens or hundreds of thousands of processing units. That's a real problem for software developers to create code that can scale to such a large number of processing units and probably scale across different compute architectures, heterogeneous architectures. So we're working very closely with Intel and Dell and Intel's new programming environment, One API, that allows us to write code that's portable and both focused on this type of application. So that's one of the areas we're looking at: code scalability and code kind of how easy it is for code to move across different exascale architectures. So that's one project. The second issue, once you have a code that can run on an exascale machine, is how can you get that I/O, that data, off of your compute nodes onto your storage, or the reverse? How can you read in data to feed such a large number of processors in a timely fashion? So storage performance is a big deal on exascale computing. So we're looking at using modern solid state storage devices and how you can fashion those in ways that can be used on exascale machines. So exascale I/O is a big problem and something we're looking at. We're looking at file systems that can be deployed on such fast solid state storage. So we're looking at file systems such as Intel Deos, and we can use Intel Deos to scale across large numbers of SSD drives and link between the SSD drives and the compute. We're looking at Lustre, looking at other ways of more low-level storage technologies to link storage hardware to the application. So that's the second area we're looking at. The third area we're looking at is the middleware, the software that's used to run that supercomputer. How can we make that supercomputer more usable to a larger number of research staff? So we're looking at modern cloud native middleware environments that sit on the machine and make that machine more usable. So we're specifically looking at OpenStack and how we can use OpenStack to create software-defined supercomputers that make that supercomputer more like the user requires in a dynamic cloud native way and allows more modern DevOps style working, which again increases the flexibility and increases the usefulness of those large scale exascale machines. The next area we're looking at is networking. Again, the supercomputer really is the network. So we're particularly interested in the emergence of Ethernet for HPC, low latency Ethernet, using open standards to really broaden the reach of supercomputing out and give more choice into the networking space. And the final area, which again is quite interesting, is visualization. Once you produce very large data sets on your exascale machine, how do you explore those data sets? How does the researcher derive value and understanding from the simulations that he's creating? So visualization is an important aspect in being able to understand the data and getting a qualitative understanding, a human understanding of the data. We don't do that through numbers, we do that through looking and seeing the data in front of us in a way that we can visually inspect it and move the data around in real time. So large scale, exascale class visualization is the final piece in that puzzle. Once you've got your data, once you've run your exascale simulation, how do you understand it? So those are the 6 different projects that the lab is working on. It's springing up now. We'll have around 20 people in the lab dedicated to these activities, split across those 6 projects, and all the outputs of the lab are going to be freely available. Everything is going to be made publicly available. There'll be a number of different reference architectures. A significant point of this lab is although we're working on technologies that are used for exascale, we want to see those technologies transferred down and out to a wider audience. So these technologies will be used to make the largest exascale machines, but also used to make machines that are much smaller, maybe a petaflop machine, but a petaflop machine which is much more affordable and usable. And all this material will be made publicly available on the website. So if you go to the Cambridge University Research Computing website and have a look there, you'll see everything we've discussed echoed there with regular updates on the projects that we're undertaking.